students, it's me Praveena. I'm here to discuss you with the topic some important parameters of optical fibers, and these parameters include V number and cutoff wavelength, Gaussian beam, mode field diameter, groove velocity and phase velocity. Let us see each parameter one by one, and first of all V number. Actually, I am discussing this because sometimes in university questions you are asked with a question, so the equations for each of these parameters will be needed. So first of all, what do you mean by V number? So V number is an important parameter that is connected with the cutoff condition of modes. Okay. So the V number is also known as the normalized frequencies, and we can explain it as a electromagnetic waves bound to optical fibers are described by fibers' normalized frequencies, and normalized frequencies determines how many modes a fiber can support, and this normalized frequency is a dimensionless quantity, and normalized frequency can be represented by V, and the normalized frequency is also known as V number. Okay. And so we can represent V number by the letter V, and its equation is given by V is equal to 2 pi A divided by lambda into NA. That is equal to 2 pi A divided by lambda into what is numerical aperture? Numerical aperture is square root of n1 square minus n2 square. So instead we can write it as 2 pi A divided by lambda into n1 square minus n2 square all raised to 1 by 2. So V number is a dimensionless quantity, and it represents the number of modes a fiber can support. And in this equation, n1 is the refractive index of the core, n2 is the refractive index of cladding, and A is the core diameter, and lambda is the wavelength of the light in air. And whenever the V number increases, the number of modes supported by the single mode and multi-mode fibers also increases. Okay. And also the number of modes supported by the multi-mode fiber is given by capital M, and it is related to the V number as capital M is equal to V square divided by 2. That is V number square divided by 2 is the number of modes, and for V less than 2.405 only one mode is supported. That means TE01 mode is only existing when V is less than 2.405. So we can say fiber is a single mode fiber in that case. Okay. So that's all about V number. Next is a cutoff frequency. So for a fixed fiber, if the light wavelength is smaller, and V number will be bigger, and a single mode fiber at a longer wavelength could support more than one mode at shorter wavelength, and the critical wavelength corresponding to the second mode to leak is called the cutoff wavelength of the fiber. Okay. So cutoff wavelength means that for a fixed fiber, if the light wavelength is small, V number will be bigger, and this implies that a single mode fiber at a longer wavelength, that means a wavelength about 1550 nanometer, could support more than one mode at a shorter wavelength, that is around 633 nanometer. So a single mode fiber at a higher wavelength can support more than one modes at a lower wavelength, and the critical wavelength corresponding to the second mode to leak is called the cutoff wavelength of the fiber, and it is defined by cutoff wavelength is lambda c, that is equal to 2 pi A into n1 square minus n2 square all raised to 1 by 2 divided by 2.405, that is the cutoff wavelength. And when the working wavelength is longer than the cutoff wavelength, the fiber is single mode, otherwise it will be multi-mode. Okay. This is all about cutoff wavelength, and it is represented by the letter lambda c. Okay, its equation is 2 pi A into n1 square minus n2 square all raised to 1 by 2 divided by 2.405. And next is the Gaussian beam, and we know that the intensity distribution of the optical beam shows that intensity is maximum at the center, and it gradually decreases towards the outside. We know it from mode theory that in the case of single mode fiber, the intensity distribution is like that. For T01 mode, we know that its intensity will be high at the center. So the intensity distribution of optical beam shows that intensity is maximum at the center and gradually decreasing towards outside. And for single mode fibers, it can be expressed by Gaussian curve. And what is Gaussian curve? It is shown in the figure, okay? And so in the case of, we know that when once we understand the propagation of modes in the fiber, we know that for T01 mode, the wave propagation waveform is like this, and this is a Gaussian beam, and it is plotted against intensity against diameter, and the intensity distribution is given by the equation I of r is equal to I0 into exponential minus 2 r square divided by W0 square. And this is all about the Gaussian beam. And next is the mode field distribution of a single mode fiber. And mode field distribution is the radial distribution of the optical power when it is propagating in the fundamental mode. And in multi-mode fiber, all the light in multi-mode fiber, all the light is confined within the core. And but in the case of single mode fiber, a portion of light, that is around 20%, is propagated through the cladding. That is why mode field diameter is important for single mode fiber, and it is slightly larger than the core diameter. So mode field distribution says the radial distribution of the optical power, and it is important in the case of single mode fiber, because in that case some of the energy will be lost in the cladding section. That represents there will be radial distribution in the cladding also. Radial distribution of power takes place in the cladding also, and whenever the core diameter increases, the mode field diameter also increases, and the relationship between optical power distributed and mode field diameter is given by E of r equal to E0 into exponential raised to minus r square divided by W0 square. And the mode field distribution of single mode fiber is shown in this figure. Left side shows a single mode fiber, and it is a step indexed fiber since its radius is given as very small 2a, and its mode field distribution is shown like this. And at the center it is maximum, and towards the left and right side it decays. And the mode field diameter is also marked as 2W0. Okay, that's all about mode field distribution of the single mode fiber. And next is phase velocity. And phase velocity means that it represents the actually it is a velocity, and phase velocity means velocity with a constant, and it is related to some constant phase, and also it is related to velocity, that is it has a name, phase velocity. So actually it represents the this velocity, the velocity that maintains a constant phase with the traveling field. Okay, once again we can say it as phase velocity is the rate at which the phase of the wave propagates in space is known as a phase velocity of a wave. Okay, phase velocity is meaning that it actually represents the rate at which the phase of the wave propagates. So actually this is the velocity at which the phase of any one frequency component of wave travels, and it also represents the velocity that maintains constant phase with the traveling field. Okay, so once wave is propagating, there will be different waves, and the phase of different waves will be different. So the phase velocity is the velocity that maintains a constant phase with the traveling field. Okay, constant phase with the traveling field. And a figure shows a amplitude modulated wave, and in that figure the modulation envelope is shown, and also the wave carrier wave is also shown there. And you can see that at the lower part we marked it as a V phase. That means the phase of that carrier wave and the phase of modulated envelope is same. That means these two, the modulation envelope and the phase of that wave, are in constant phase with each other. So the velocity at which these two waves moving is called phase velocity. So we can say that clearly that phase velocity, the velocity that maintains a constant phase with the traveling field. So that is the phase velocity. And also we can say a monochromatic wave. What do you mean by monochromatic wave? It has a common angular velocity and wavelength. So single omega and wavelength monochromatic, and that travels along the fiber axis is described by the equation E of t comma x is equal to E of exponential raised to j omega t minus beta x, where E is the amplitude of the field and omega is 2 pi f, and here beta is propagation constant. Actually it represents a monochromatic wave, and its equation is E of t comma x, that is equal to E into exponential raised to j omega t exponential raised to j omega t minus beta x. Omega is 2 pi f and beta is propagation constant, and here E represents the amplitude of the field, and beta is the propagation constant, and we can say phase velocity, which is represented by v suffix p, and the phase velocity Vp is defined as the velocity that maintains constant phase with the traveling field, and that means omega t minus beta x is equal to constant. That is in the equation omega t minus beta x is constant, that means its phase is constant, and in that equation x is the traveled distance, and that traveled distance is calculated within time, and x is equal to, so the travel distance can be written as x is equal to Vp into t, and the phase velocity of the monochromatic light in the medium is given by Vp equal to omega divided by beta. So that is the equation that we are interested in, that is phase velocity equation is phase velocity Vp equal to omega divided by beta, where omega is angular velocity, that is equal to 2 pi f, and beta is a propagation constant. Okay, so that is equation for phase velocity, and also in the diagram we can mark the phase velocity as the velocity that maintains a constant phase with the traveling electric field. So we are marking the phase velocity here. So, and next is the group velocity. Usually a pure sine wave that cannot convey any information, and so for conveying it for conveying information on the sine wave, and some changes in amplitude or frequency should be there, and if we are changing amplitude or frequency of the sine wave, then that technique is called modulation. So for changing that frequency or amplitude, modulation is required, and by combining two sine waves with slightly different frequencies and wavelength, the amplitude becomes a sinusoidal pulse, amplitude becomes a sinusoidal, okay, and with a phase speed is equal to d omega divided by d beta, and it is a modulation that represents the signal content, and since each amplitude envelope contains a group of internal waves, this speed is usually called the group velocity. See in the previous figure we can see that it is marked phase velocity at the lower side and group velocity is marked on the envelope, okay. And here once again I am stressing the point, by combining two sine waves with slightly different frequencies and wavelength, the amplitude becomes a sinusoid with phase speed d omega divided by d beta, and it is so because the phase speed is d omega by d, it is called d omega by d beta. We know that from the previous case the phase velocity Vp will be w omega divided by beta. So here when we are combining both this, and the phase speed will be d omega divided by d beta, and the modulation represents the signal content, and since each amplitude envelope contains a group of internal waves, this speed is usually called the group velocity Vg. And group velocity of a wave is the velocity with which the overall envelope shape of the wave's amplitude propagates through fiber. So what do you mean by group velocity? A group velocity of a wave is the velocity with which the overall envelope shape of the wave's amplitude propagates through fiber. So I can explain it. We know that this is the amplitude modulated wave, and in that we know that we are, in the case of amplitude modulation, we are superimposing carrier with a modulating signal. So the resulting wave will have the same shape as that of the original signal, but it contains two signals, so that is scatter and original message signal. You know that, and there will be two signals inside this signal. So when this original field is traveling, these two waves also will be traveling. So that velocity is known as a group velocity. That is defined in this case. Like since each amplitude envelope contains a group of internal waves, that is right, because each amplitude in the figure, each amplitude will contain a group of waves, because we are using modulation technique. It will superimpose a carrier wave with modulating wave. So each amplitude envelope contains a group of internal waves, and so the speed of traveling wave will be equal to the group velocity. That means a group velocity of a sine wave is the velocity with which the overall envelope shape of the wave's amplitude propagates through fiber. So the overall envelope travel ചെയ്യുന്ന ഒരു ഫൈബറിലൂടെ ഒരു സൈൻ വേവിൻ്റെ ഓവറോൾ എൻവെലപ്പ് ട്രാവൽ ചെയ്യുന്ന സ്പീഡിനാണ് എന്ത് പറയുന്നത്, ഗ്രൂപ്പ് വെലോസിറ്റി എന്ന് പറയുന്നത്, റൈറ്റ്? ബിക്കോസ് ആ ഒരു എൻവെലപ്പ് എന്ന് പറയുന്നത് സിംഗിൾ സൈൻ വേവ് അല്ല, ഇറ്റ് ഇസ് ഗ്രൂപ്പ് ഓഫ് സൈൻ വേവ് ആണ്, ഓർ 1 or 2 സൈൻ വേവ് ആണ്, കോമ്പിനേഷൻ ഓഫ് 1 or 2 സൈൻ വേവ് ആണ്. അതുകൊണ്ടാണ് അതിനെന്ത് പറയുന്നത്, ഗ്രൂപ്പ് വെലോസിറ്റി എന്ന് പറയുന്നത്. ആൻഡ് ഓപ്റ്റിക്കൽ വേവ്സ് ആർ ട്രാവലിംഗ് ആസ് വേവ് പാക്കറ്റ്സ്, ആൻഡ് ദീസ് വേവ് പാക്കറ്റ്സ് ഹാവ് ഗ്രൂപ്പ് വെലോസിറ്റി Vg. And group velocity is indicated by the letter Vg, and that is given by the equation d omega divided by d beta. So group velocity is d omega by d beta, and phase velocity is omega by beta. Okay, phase velocity എന്ന് പറയുമ്പോൾ കോൺസ്റ്റൻറ്റ് ഫേസ് ട്രാവലിംഗ് വേവ് ആയിട്ട് കോൺസ്റ്റൻറ്റ്, ഒറിജിനൽ മാഗ്നറ്റിക് ഫൈബറിലൂടെ തന്നെ ട്രാവൽ ചെയ്യുന്ന വേവിനായിട്ട് കോൺസ്റ്റൻറ്റ് ഫേസ് മെയിൻറ്റെയിൻ ചെയ്യുന്ന വേവ്സ് ഉണ്ടാവുമല്ലോ, അതിൻ്റെ വെലോസിറ്റിയാണ് ഫേസ് വെലോസിറ്റി എന്ന് പറയുന്നത്. അതേസമയം ഗ്രൂപ്പ് വെലോസിറ്റി എന്ന് പറയുന്നത് ഈ മൊത്തം എൻവലപ്പിൻ്റെ വെലോസിറ്റി ആണ് എന്ത് പറയുന്നത്, ഫേസ് വെലോസിറ്റി, സോറി ഗ്രൂപ്പ് വെലോസിറ്റി എന്ന് പറയുന്നത്. ദാറ്റ് ഈസ് ദി ഡിഫറൻസ് ദാറ്റ് യു ഹാവ് ടു സ്ട്രെസ് ഔട്ട്, ആൻഡ് യു ഷുഡ് അണ്ടർസ്റ്റാൻഡ് ദി കോൺസെപ്റ്റ് വാട്ട് ഈസ് ഫേസ് ആൻഡ് വാട്ട് ഈസ് ഗ്രൂപ്പ് വെലോസിറ്റി. ഓക്കെ, that's all about this topic, and next we will meet with another topic. Bye.